Welcome to Power Electronics Education Electronic Book, Lecture 8, DC-AC Converters. This lecture is presented by Dr. FIRUZ ZARE. So in this lecture, we have three main subjects. Introduction, basically talking about general concepts in inverters, which is current source or voltage source inverters, single phase or three-phase inverters, modulation strategies, two-level or multi-level converters, and closed loop or open loop control, and then bipolar and unipolar modulations in single phase inverter, and finally different concepts in three-phase inverter. So in an inverter, we convert the DC voltage to an AC voltage. For example, if we have a DC voltage coming from a battery, then we can generate positive voltage for half a cycle, and then we can generate negative voltage for second half a cycle. So in this case, we can see that the DC voltage is changed to AC. That means we have positive pulse here and negative pulse here. So this one is not pure sine wave, which means it has harmonics, but basically we can remove the harmonics by a filter. So in this case, if we look at the output here, voltage and current, for example, for this period, we can see that the current is negative, but the voltage is positive. That means the system operates in this quadrant. And because of positive voltage across the RL load, so the current is getting positive. So now for this interval, current is positive and voltage is positive. That means we move to this quadrant. And once the output voltage is getting negative, so for this period again, still the current is positive, but still in this case current is decreasing. That means current is positive but voltage is negative. So we move to this quadrant. And because of keeping the negative voltage across the RL load, so the current is getting negative for this period, and voltage and current both are negative. So in general, RL load operate in 4 quadrants. So that means the system should be able to provide positive and negative current and also generate positive and negative voltage. When we talk about voltage source inverters, we can generate DC voltage, we can provide DC voltage using a large capacitor, or we can generate current source using a large inductor. So because inductor is very large, that means it's very bulky and expensive and heavy. So that's why in this case, operating at high power applications, we need to have large inductor. And in this case, instead of bidirectional current switch, we need to have a diode in series with the switch to be able to handle positive and negative voltage across the switch. And this one, in voltage source inverter, we need to have anti-parallel diode with the switch in order to provide positive and negative current. So in most applications, we have voltage source inverter. So the question is that how we get the power supply, the DC voltage. It can be a battery, it can be PV, or it can be a rectified voltage coming from grid or wind generators. So the point is that because of harmonics, we can normally use capacitor to be able to remove the ripple. But in some applications, because the battery's voltage is not enough for high voltage applications, we may need to have DC-DC converter to boost the voltage, or even the PV's voltage is not high enough, we can have DC-DC converter. Or even in rectifier, because the output voltage has ripple, it doesn't matter single phase or three phase, then in this case we can also have a capacitor. So that's why basically when we are talking about voltage source inverter, we have a capacitor as a voltage source. So when we have a battery or when we have a PV, because the voltage is not high enough, we may have boost converter to be able to increase the voltage, and basically we have a capacitor at the output of the boost converter. So in this case the power supply is defined as a capacitor in most of inverters. And if we have a rectifier, for example here, if you look at a single phase rectifier, to improve the output voltage, to reduce the ripple, we may need to have a capacitor. So that's why this capacitor is a voltage source for the inverter and is a filter for either rectifier or DC-DC converter. So that's why when we define a capacitor, that means we have a source, voltage source here, which can be as a PV, battery, or grid voltage through this diode rectifier. So when we have two converters in cascade, we can see that the system can change the phase. That means if the input voltage is single phase, and if you have diode rectifier to get DC voltage, and then we can have DC voltage for this inverter as a voltage source, and here we can generate either single phase or three phase. That means this process, that means these two converters in cascade can change single phase to single phase or three phase with variable frequency and variable voltage. That means we can either control the voltage and frequency, and also we can change single phase to single phase or three phase. And it's also true that we can also change three phase to three phase or single phase, depends on the application, and also depends on the power rating. So here we can see that using two converters in cascade, when we have grid voltage either at 240 single phase or three phase, so we can change the output voltage. That means the voltage can be changed from 0 up to, for example, 240 again, variable voltage, especially for motor drive applications, or the frequency can be changed up to 50 or even more, depends on the application. Now let's look at the circuit diagram. So when we are talking about voltage source inverter, so here we have capacitor which provide DC voltage for this inverter. And when we are talking about single phase inverter, basically we have two legs, leg A and leg B, and this is the load. So we expect to get AC voltage across the load. This is output voltage. And when we have three phase, again here we have voltage source, and we have three legs, leg A, leg B, and leg C, and this is the load, three phase load. So the point is that we can generate AC voltage at these terminals, which can create phase voltage for each load. So modulation strategies are very important in power converters, because we can generate AC voltage, for example, with single pulse. So in frequency domain we have fundamental plus harmonics, so we expect that this is the fundamental of this signal plus harmonics. So the case is that we can improve the output voltage by increasing the switching frequency or increasing the number of pulses. For example, if we look at the output current for this type of voltage waveform, suppose that we have resistive and inductive load. From here to here, we can see that there is no current, and from here to here, because of positive voltage we have, we can increase the current, and from here to here, because the voltage is zero, the current through the inductor is discharged through the resistor, and then we have negative, again the current is decreased. So here, because the output voltage is zero, here we can see that the current is decreased and then increase. So this is the current waveform. Approximately we can draw the output current. But what's the difference when we increase the number of pulses? So here, for example, when the output voltage is zero, then we have a small pulse, we increase the current, and again the output voltage is zero, the current is decreased a little bit, and then we increase the current is decreased, and then we increase the current, decreased, we increase the current because the voltage is positive, the current is decreased because the voltage is zero, and then we increase it, decrease, increase, and then decrease. And here we have negative voltage, so the current is decreased. So again, because the voltage is zero, current is decreased. So here we have negative voltage, so current is decreased. So now here we can change the current, sketch the output current, and here you can see that the shape of output current is more to sinusoidal than the compared to that one. And why is more sinusoidal? And that's because we have more pulses, which can improve the output voltage and output current. So in this section we look at the control section, because the power switch, for example either an IGBT or MOSFET, we need to provide gate signal for the switch to be able to turn on and turn off. So in this case, using a comparator, we can compare DC voltage with the triangular voltage waveform, and based on that one we can change the pulse width. That means by increasing or decreasing the DC voltage, we can get wider pulse, or we can change the pulse width. So this is one method that we can control the pulse width for some applications. So by changing the switching frequency, we can increase the number of pulses. For example, here we can define switching frequency. That means starting from this point up to that point is defined as one switching cycle, which is given here, and this one equals to 1 over FSW. So this one is switching frequency. So we call that one as a carrier signal. So changing the frequency of carrier signal means we have more pulses. That means we increase the frequency of the signal. So as I mentioned before, to improve the quality of output voltage, we need to have more pulses, or the switching frequency should be increased. So a common method is sinusoidal pulse width modulation. That means we compare a sine wave with triangular voltage waveform, and using this comparator we can generate gate signal. So the point is that here we have switching frequency, which is defined the switching frequency of this carrier, as I described before, is 1 over switching frequency equals to switching cycle. So the point is that by increasing the switching frequency, definitely we can improve the quality of output voltage, reduce the total harmonic distortion but the drawback is we increase the switching losses. So another method to control the output voltage and reduce the harmonics is based on harmonic elimination technique. That means in this case we define these switching times, and we can find the pulse width based on Fourier series expansion. So in this case we can pre-calculate the harmonics and find this switching time to be able to, for example, reduce the third harmonics, fifth harmonic, and so on. So that's why in this case this is like an offline switching method, because we need to calculate this one before and store the switching time in a memory or in a microcontroller and then run the program. So basically this method is very useful for open loop control when the output voltage is not changed significantly. So what's the difference between two-level and multi-level? So basically two-level is very common, because if you look at the power supply, we get DC voltage across the DC source. So in this case we can either get zero voltage or positive DC, because we have only one capacitor, one power supply. We can generate multi-output. That means instead of two voltage levels here, we can have multi-voltage levels. So what's the advantages? The advantage is that we have less voltage stress across the load. For same voltage rating, we may get less voltage stress. And also because of changing the output voltage step by step, then we can improve the quality and also less switching losses. Another case is that multi-level converter is a suitable converter for high voltage applications, but the drawback is that the circuit diagram and the control method is very complex for multi-level converters, especially when the number of levels is increased, and also we need more components. So what's the difference between closed loop and open loop? Basically in open loop we normally generate the gate signal without measuring the output voltage, and in this case we can run different algorithms to generate different pulse pattern. But in closed loop control we can measure the output voltage or output current, and then based on the reference signal, controller can generate a proper gate signal. So to understand single phase or three phase converter, let's start with one leg inverter. One leg inverter basically consists of two switches here, in which when one of the switch is on, the other switch should be off. So basically we define switching state based on the top switch. That means when the switching state is defined as 1, that means that switch is on and the other switch should be off. And because in power electronics the switch should be able to handle bidirectional current, so that's why the switch itself is defined as an IGBT or MOSFET with antiparallel diode. So this is a switch which can handle bidirectional current. So let's start with this voltage waveform. For example, we're trying to measure the voltage across these points or this terminal with respect to this neutral. So when S1 is on, that means we have gate signal for S1 and there is no gate signal for S2. So in this case S2 is off and S1 is on. So when S1 is on, so this voltage, this terminal is connected to this voltage. That means the output voltage is positive, VDC/2. That's why we have this voltage. And when the switch is off here we can see that there is no gate signal for this switch, while we have a gate signal for that switch. So in this case, this terminal is connected to this voltage. So that's why the output voltage is minus VDC over 2, which is shown here. In a single phase inverter, we have two legs, leg A and leg B, and this is a load. So as I mentioned before, because we define the switching states based on the top switches, so in this case we have two switches. That means there are four different combinations. When top switches are off, when S3 is on or S1 is off, when S1 is on, S3 is off, or when both are on. So in this case we have four different switching states and three different voltage waveforms. That means for this case and this case we get zero voltage across the switch when these two switches are on or these two switches are on. So we get minus VDC when this point is connected here and this point is connected here when these switches are on. We get plus VDC when this terminal is connected here and this terminal is connected here. So that's why we define bipolar and unipolar modulation for single phase inverter. Bipolar means that the output voltage just change between minus VDC and plus VDC, but unipolar, the output voltage is changed between 0 and plus VDC or 0 and minus VDC. So let's see the current and voltage waveforms for bipolar modulation. So starting with this switching state, that means S1 and S4 are on, these two switches, and S2 and S3 are off for this interval, just this interval. But in a steady state, we can see that for this short period, the current is negative while the output voltage is positive. So output voltage is positive because this switch is on, and because the current is negative, so this is the direction of current. So in this switch, because this switch is on but it cannot handle the current because of direction of current, so in this case current passes through the diode. So this terminal is connected to plus VDC, and in this case this diode also conduct, so this terminal is connected to minus VDC. So here we can see that the output voltage is positive VDC while the current is negative. That means this is the current loop. And once the current is getting positive, here we can see that because the direction is changed, so the IGBT is turned on, now it can handle. So the current passes through the IGBT or switch inside the main switch, and the current is positive. That means this IGBT also can handle the current. So that's why for this period here, when the current is positive, current passes through these switches. So when the output voltage is getting negative for this period here, we have two sub periods here. For example, this short period when the current is positive while the output voltage is negative. So because the output voltage is negative and current is positive, so this is the circuit diagram and this is the current loop. So that means in this case still current passes through the diode, and this is the load. It's better to define the polarity plus minus V out. So in this case the output voltage is negative, so current passes through the diodes. But at this point the current is getting negative. That means output current and output voltage both are negative. So in this case, because current is negative according to this definition, so this is the current loop. That means the IGBT here and this IGBT can conduct, and the current pass through IGBT load and pass through the second IGBT. So in bipolar modulation, when we have only one pulse, so it's possible to change the frequency, but it's not possible to change the RMS output voltage. So in this case, we can only change the RMS by changing the DC voltage, which is not possible because in most of applications the DC voltage is constant. So in this case, by changing the switching time, we can change the switching frequency and we can change the output frequency, but the RMS is basically depends on the magnitude of DC link voltage. But if we increase the switching frequency, that means over one cycle, if we have so many pulses instead of one pulse, then it's possible to change the frequency and voltage. So when we increase the switching frequency, so here you can see that this defines as a switching time, which is equal to 1 over switching frequency. So by increasing the switching frequency, we can change the frequency and RMS of output voltage. So in this case, in the control section, we compare a sine wave with a triangular voltage waveform, and then we get gate signals for different switches. So here we can see that not only we can improve the quality, but also we can control the frequency and magnitude of output voltage. So let's look at the output voltage when we increase the switching frequency. So this is the voltage of leg A with respect to midpoint. So the output voltage sometimes is positive 50 and negative 50. And leg B is also the output voltage is changed with respect to neutral point. And output voltage here is VA minus VB. So for example, when for this interval here, we can see that the output voltage in leg A is 50 and leg B is here minus 50. So that's why this voltage is 100, which is given here. And for this interval, for example, the leg A is minus 50 and leg B is plus 50. So that's why output voltage is minus 100, which is given here. So this is the output voltage waveform, and we can see the effect of switching frequency. Even if we increase the switching frequency more, so we can see that the ripple is decreased. So this is output current. So if you compare this current waveform with this current waveform, we can see that there is a significant change between this waveform and this waveform. This case has more switching losses, while this one has less, but the ripple is more than this method.